Welcome to thermodynamics course. Question of states is the last topic of chapter 2. The relationship among state variables, that is temperature, pressure, and a specific volume is called equation of state. So using this equation of state, we can relate temperature, pressure, and a specific volume. And there are several equations of states. Some of them are simple and others are very complex. And the simplest and best known equation of states for substance in gas phase is the ideal gas equation of states, and it is PV is equal to RT. So this equation predicts PVT behavior of a gas quite accurate within some properly selected region. So that if we have this equation or equation of state PV is equal to RT, so we can determine or calculate one of the state variables like pressure, temperature, or specific volume. Based on our experience in chemistry and physics, we recall the combination of Boyle's and Charles' laws for gas, and from these two laws we have this relation: PV is equal to R times T over V. It's a well-known equation from these two laws. So we can rewrite this equation in this form: PV is equal to RT. P is temperature, V specific volume, and R is gas constant, and T is temperature. Again, we can rewrite this equation in the form of this one. That means just instead of a specific volume, we can use volume and mass in this side, which means volume over mass is equal to a specific volume. Then PV is equal to mRT. Or in other way, instead of mass, we can use mole number and molecular weight. So these two relation gives mass. Then again, PV is equal to nmRT. The constant of proportionality R is called gas constant, and the gas constant R is different for each gases, and it's determined from this relation. R is equal to universal gas constant over mass, and the unit of R or gas constant is kilojoule per kilogram per Kelvin. So whenever we use this relation, we have to consider these units. R is always in this form, kilojoule per kilogram times Kelvin. So for example, for pressure we have to use kilopascal, and for temperature we have to use Kelvin because R is in this form. Otherwise, for example, if we use degree centigrade for temperature, then we are making a big mistake because R is in Kelvin and T is in degree centigrade. Then the result is so far from the exact one. Where RU is the universal gas constant, and its value is around 8.31 for kilojoule per kilomole Kelvin, and mass M, capital M, is molar mass, also called molecular weight. So using these two values, we can determine the gas constant of any gas. And again, M is equal to N times molar mass. The ideal gas equation of states can be written in several different forms. For example, volume is equal to mass times specific volume. Then from this relation, from PV is equal to RT, you can write PV is equal to MRT. Or MR, that means mass times gas constant, means molecular weight times molecular number, N. So instead of MR, maybe you can write NRU, which means RU is R times M. So instead of MR, maybe you can write mole number times universal gas constant. Then from this relation, we can rewrite PV is equal to mole number times universal gas constant times temperature. Again, we have another form. Volume is equal to molecular mole number times specific volume per mole number. If there is over slash, which means this number is per mole. Okay, so N times V will give us volume. Then again, from instead of this equation, we can rewrite in this form: V is equal to NV, then PV is equal to RU over T, which means V over bar means volume over mole number. Then we have this relation. The properties of an ideal gas at two different states are related to each other by this equation. Q1 V1 over T1 is equal to P2 V2 over T2. So if we have two different states, state 1 and state 2, so using this relation or equation, you can relate these two different states, Q1, state 1 and state 2. And these are substances that consider as ideal gas: air, nitrogen, oxygen, hydrogen, helium, argon, and there are also other substances, but these are the basic and mostly used ideal gas substances. And the other topic is compressibility factor, or measure of deviation from ideal gas. From previous slides, we have seen equations that relates state variables. PV is equal to RT. Okay, so it's a simple relation, just PV is equal to RT. Let's say we have pressure and temperature. So we have only these two properties, and we would like to know the other property, volume. Okay, so determine the volume of this substance from these two property, pressure and temperature. Just using the ideal equation, PV is equal to RT, we can determine, just short and simple. But if the substance is not ideal gas, we have to use table. Again, we have pressure and temperature. So first we determine the state, because to use the table, first we have to determine the state. So then after we determine the state, we can read the volume from table, or we calculate after we determine the state. So it's a little bit long steps compared with the ideal gas. So we try to assume either other substances as ideal gases, which means just we have PV is equal to ZRT. Okay, the previous equation was PV is equal to just RT. There is no Z in the front of RT. So Z stands for a measure of disorder from ideal gas. Just we are trying to approximate the substance as ideal gas using this Z factor. compressibility factor. For real gas, Z can be greater than or less than 1 or unity. Okay, if Z is equal to 1, then the gas is ideal gas. That means just PV is equal to 1 means just RT. So if the substance is real gas, then Z will greater or less than 1. Now we have this graph. In the y-axis, we have Z value, which is compressibility factor, and in the x-axis, we have reduced pressure or PR, and we have different curves in the graph, and that are TR, reduced temperature. Okay, so TR at different value and PR at different value and Z at different value. PR means given pressure divided by critical pressure of that substance, and TR means given temperature divided by critical temperature of that substance. Okay, so if we have these two values, PR and TR, then we can read the value of Z from the graph, and we can use this relation PV is equal to ZRT. Z for this compressibility factor or measure of disorder. We are assuming real gas as ideal gas, so we have a correction factor Z. So this Z value read from this chart using PR and TR. PR and TR are obtained from this relation. PR is equal to P over P critical, given pressure over P critical, TR given temperature over critical temperature. And this graph work for these different substances: methane, ethyl, ethanol, propane, and butane, and so on. But for water, we have this graph just for simple fluid, or just water also a simple fluid, so we use this graph. It's the same as the previous one. We have Z in the y-axis and PR or reduced pressure in the x-axis, and we have different TR values in this curve. Okay, so using this PR and TR, we raise the value of Z, then we can use PV is equal to ZRT relation for real gases. Now let's see some example on this subtopic. Example 1. Determine the mass of the air in a room whose dimensions are 4 meter times 5 meter times 6 meter at 100 kilopascal and 25 degree centigrade. So this is our room. We have a 5 meter height, 6 meter width, and 4 meter depth, and the room is filled with air at P is equal to 100 kilopascal and T is equal to 25 degree centigrade. So the only, and we are asked to determine the mass of the air in this room. And we have this gas constant for air, R is equal to 0.287 kilojoule per kilogram times Kelvin. It's given, or we can read from any thermodynamics table. Now, this is our given dimension: 4, 5, 6, pressure 100 kilopascal, temperature 25 degrees centigrade, and we have to find the mass of the air in that room. First, let's change this temperature into Kelvin, because our pure substance is air, so we can use the ideal gas equation because air is ideal gas. So to use the ideal gas equation, we have to change this degree centigrade into Kelvin. Otherwise, the answer will be wrong because R is given in Kelvin here, so we have to convert this into Kelvin. Okay, air treated as an ideal gas, and we have R this much. Okay, from ideal gas equation, PV is equal to mRT. V stands for specific. V stands for volume because we have here mass, so V is volume, not a specific volume. If this one is specific volume, then there is no mass here. Okay, so this is volume. So P is given from here, R given, T given. So mass we have to determine, that's the equation, and volume we have the dimension of the room. So from this dimension we can calculate the volume, and V is equal to 4 times 5 times 6, it's around 120 meter cube. So we have all values, only mass. Then M is equal to, from this relation, PV over RT. Now let's substitute the values. P 100, V 120, R 0.287, and T 298. Then finally we can calculate the mass of the air in this room. M is equal to 140 kilogram. So using just ideal gas equation, you can determine any unknown from this relation, P or V or T or M, using this relation. Okay, just a simple calculation. There is no table to use or to determine the state. Example 2. A piston cylinder device initially contains 0.2 kilogram of steam. Okay, initially contains 0.2 kilogram of steam at 20 kilopascal and 300 degrees centigrade. Then state 1 is 200 kilopascal, pressure P1, and T1 is equal to 300 degrees centigrade. Now the steam is cooled at constant pressure. The process is at constant pressure, then P is constant until temperature T2 is equal to 150 degrees centigrade. Determine the volume change of the cylinder during this process using the compressibility factor, and compare the result to the actual value, which means it's water, so we can use table, and the table value is the actual value. So using 2 meters we try to determine change in volume, because at the initial state we have steam in this piston cylinder device. Then there is some heat exchange between the system and the surrounding, so our system lose some heat. So due to this heat loss, the volume will reduce. So determine the volume change of the cylinder using 2 methods, the compressibility factor method and its actual, that means using table methods. So it's a long step, so let me use a PDF this one. No. Okay. Now, first let me use the actual method. Given we have mass 0.2 kilogram and state 1 steam at 200 kilopascal and T1 300 degrees centigrade. These are state 1 properties. Now at constant pressure the system lose some heat or subcooled. So the pressure is constant, P2 is equal to 200 kilopascal, and the final temperature is T2 is equal to 150 degrees centigrade. So we have state 1 and state 2. Now the unknown is, or the asked question is to determine the volume change, which means first we have to determine volume 1 using these two properties. Then we determine volume 2 again using these two properties. Then from these two volume we can determine the change of the volume. State 1 is steam, it's given. So just from superheated table, let's go to table. Okay, superheated water. The properties are 200 kilopascal and 300 degrees centigrade. 200 kilopascal means 0.2 megapascal. This one 0.2 megapascal, and temperature is equal to 300. Okay, then volume is equal to, at P is equal to 0.2 megapascal and T is equal to 300 is much. Specific volume is equal to 1.31623 meter cube per kilogram. Okay, so volume is equal to this much, 1.31623 meter cube per kilogram. State 2, P2 is equal to 200 kilopascal and T is equal to 150 degrees centigrade. So first we have to determine the state. So using graph method or any other method we can determine the states. First let me fix the temperature 150. So at T is equal to 150, P sat is equal to, from table, make your table, at T is equal to 150, T is equal to 150, P is equal to, P means P sat is equal to 476.16. Okay, and the given temperature pressure is equal to 200, which means it's less than P sat, then the state is superheated. Again, from superheated table, at P is equal to 200 kilopascal and T is equal to 150, we can read the value of specific volume. Let's go to superheated table. At P is equal to 0.2 megapascal and T is equal to 150. The value of specific volume is equal to 0.95986 meter cube per kilogram. Okay, this much. So we have the two volumes, V1 and V2. Now we can determine the change in volume. Change in volume is equal to V1 over V2. Okay, but these values are specific volume. To convert into volume, you have to multiply by mass, and the change in volume using the actual method is equal to 0.07128 meter cube. So this is a change in volume due to this heat loss from this piston cylinder device. Now let's calculate the change in volume using the compressibility factor. That means P is equal to ZMRT. Now to calculate V1 with state 1 volume from this relation, Z times MRT over P. Here we have 1, 1, 1 subscripts for state 1. Okay, mass and R are the same because R is depend on the substance, so the substance is the same, it's water, so we have the same R value for state 1 and state 2, and again M also we have the same M value for state 1 and state 2 because our system is a closed system, there is no mass transfer, then mass is constant and R also constant. For water, R we can read from table, and you can get this table from any thermodynamics book appendix, or from the webpage junakacho.wordpress.com webpage under thermodynamics category. Go to reference book. Okay, then from the reference book there is a list of books, and here we have thermodynamics table. Okay, so from this table you can obtain from this. So we can download from this, or we can obtain from any thermodynamics book appendix. Now let's read the value of R. Here, mole mass, gas constant, and critical point properties for different substances. And our substance is water. So for water, R is equal to this much, 0.4615 R value, or gas constant value. Okay. Also, we can read the value of P critical temperature, or P critical, or volume critical if it's necessary. Okay. So from this table we have the value of PR. R is equal to 0.4615 kJ per kilogram, and PR again from this table, TR 647.1 and PR 22.06, P critical and T critical. Okay, so you can take these values, PR and TR. Okay, now we are trying to read the value of Z. To read the value of Z, we need these two values, PR and TR. PR, P, the given pressure over P critical, and the given pressure for state 1 is 200 kilopascal, and P critical from table is this much, megapascal, so we have to convert into kilopascal, then 22,016 kilopascal, and the value of PR is equal to 0.0091. Again, TR, temperature also in Kelvin, so we have to convert it into the given temperature into 2 Kelvin. Okay, again TR is equal to T1 over T critical, which means 300 plus 273. We are converting into Kelvin divided by T critical, and it's around this much, 0.886. Now, using these two values, P, R, and TR, we can read Z from the previous charts. This chart. Okay, let me remind you the values, PR and TR. PR 0.0091, 0.0091. We have 0.1 here, 0.01 here, so 0.099 almost around here, almost here. And TR 0.886, 0.886, 0.885, 0.9. So between these two lines, it goes to like this. Okay, so it's almost 0.99 or 0.9. Here 0.8. it's around 0.98, okay, 0.8, 0.9, 0.95 here, then 0.99, okay, but I wrote here 0.9, okay, let's take 0.9, there's a little variation. Now let's substitute all the values in this equation. V1 is equal to ZMRT over P. Okay. V1 is equal to 0.1. Z value, we read from chart. Mass, it's given 0.2. R, we read from table for water 0.4615. And T1, it's given. And P1, it's given. So V1 is equal to 0.26 meter cube. Again, for state 2, using the same procedure, we can calculate V2. Okay, first, the only mass is constant for state 1 in state 2, R constant for state 1 in state 2. So we use T2 for state 2, P2, and we read Z2. Then we can determine V2. Okay. PR2, to read the value of Z2, first we have to calculate PR2 and TR2, reduced and T reduced. And PR2 is equal to the given pressure, P2 over P critical. Okay. So P2 is constant, 200. Yeah. P2 is constant, 200, and P critical, read from here. Then PR2 is equal to 0.091. TR2, again from given temperature, T2 divided by T critical. Then given temperature is 150 in state 2, so we have to convert it into Kelvin. And T critical for water, read from table. Then using these two parameters, Z2 is around 0.98. Then using V2, using this relation, after substituting the values, we can determine V2 is equal to 0.132 meter cube. Now, change in volume is equal to V1 minus V2, 0.07 meter cube. If you compare using these two methods, the actual method gives change in volume is equal to 0.07128 meter cube, and the approximate method gives this much, 0.07. Almost they are the same. And percent of error using this approximate method, or the compressible charge method, error is equal to changing value divided by the true value. Then it's almost 1.7% error introduced using this compressible factor. So if we don't have the thermodynamics table, maybe sometimes we can assume real gas or real substance as ideal gas using this compressible factor Z. Then this is the solution for example 2. Thank you for your attention. I will stop the lecture for state equation.